Hello, ladies and gentlemen. Today we are going to be taking a look at equilateral and isosceles triangles. For our work today, you're going to need your foldable that we'll go ahead and place in your notes in a little bit, as well as your calculator. We're working on filling out this foldable today about special properties involving isosceles and equilateral triangles. So first we'll start with some vocabulary, then we're going to take a look at the base angles theorem and its converse, as well as the corollary to the base angles theorem, which just means an extension of that base angles theorem. So first let's start with some vocabulary here. You have this picture in your notes, and let's go ahead and add in some terms. This is an isosceles triangle here. There are special names for these two sides here that are congruent. So the two sides, I think I should draw one over here too. The two sides that are marked congruent are called the legs. And underneath that I would write that they are the two congruent sides. The third side down here is called the base. It's the one that isn't congruent to the other two. Near the base now, we have two angles down here on the bottom. It doesn't always have to be on the bottom. The triangles turn, as you know, but they will always be the ones that are on the side that we would call the base, whether the triangle is turned or not. These angles here and here are called the base angles because they are adjacent to the base or next to the base. And they will always be congruent to each other, there and there. At the top of the triangle, this angle also has a name. It is called the vertex angle. It's not a base angle, but it's called the vertex angle. So we have isosceles triangles have two legs here that happen to be congruent. They also will have two congruent base angles. And the base angles, again, are adjacent to the base. So with that vocabulary in mind, let's take a look now at that base angles theorem that I was hinting at and its converse. And it's the reverse of it, essentially. So first, the base angles theorem. It says if two sides of a triangle are congruent, then the angles opposite them are also congruent. So if we have two congruent sides, then those angles across from them will also be congruent to each other. Now, that makes sense, but the angles across from them will be the base angles of every triangle. So with that in mind, let's go ahead and make a little note right here. The angles that we are talking about are the base angles. They will always be congruent. So now let's look at a couple examples here. So if this is the triangle we're dealing with in number 1, I can see the two congruent marks here. Those are the legs. That means the third side up on top in this case happens to be the base. This side is the base. Now with that in mind, these angles adjacent to the base here are called the base angles. Again, they are the ones that are across from the two congruent sides. Those base angles will be congruent to each other. So if we were to set up some algebra here to solve, we'd say the 7x plus 2 angle has to equal the 8x minus 7 angle. And then get your x's together here on one side. We'd have 2 equals x minus 7, add 7, so x would equal 9. So if x is 9, now how do we find y? Notice that y is down here in the vertex angle. The vertex angle isn't necessarily congruent to anything else, but if we know that the x is 9, we can go ahead and calculate what the other two base angles are. So I'm going to take this 9 and plug it back in here. We'd have 7 times 9 plus 2. So we'd have 7 times 9 is 63 plus 2 makes 65. So each of the base angles are 65 degrees. 65, 65. Together that makes 130. So that means 2y right here, this angle, has to be 50 degrees because that's what's left over from my 180 degrees in my triangle. So I'd set 2y equal to 50 and the y becomes 25. Let's take a look at another example, example 2 here. The two base angles in this picture will be congruent. So 2x plus 4 equals 4x minus 22. And we'll go ahead and solve. We'd end up with 4 equals 2x minus 22. So if I add 22, I'd get 26 equals 2x. X is 13. So if we plug it into one of the base angles, if the x is 13 and I plug it back in up on top, I'd have 2 times 13, which is 26, plus 4 more makes 30. So each of these base angles here, 30 degrees. So 30 degrees and 30 degrees makes 60 degrees. That leaves me with 120 degrees up on top here for that vertex angle. So if I set 4y equal to the 120, divide by 4, y would be 30 degrees. Okay, so solving for x and y in these types of triangles involves us knowing which angles are congruent. Let's look at the converse. The converse says, well, what if you know that the two angles of the triangle are congruent? Well, the same relationship follows. If the two angles of a triangle are congruent, then the sides opposite them will be congruent. So this angle and this angle are the base angles. They are congruent to each other, which means this is an isosceles triangle that has two congruent legs. So if I look across from that base angle and across from this base angle, I would know that 5x plus 7 has to equal 42 because those are the two congruent sides. So if I subtract 7, 42 minus 7 is 35, and divide by 5, x is 7. Looking at example 4 over here, be careful. Just because you have 3 sides doesn't mean you add them together and set it equal to 180. These are sides, not angles. I have two congruent angles, which means I will have two congruent sides. The two congruent sides will be this one and this one because those will be across from the congruent angles, and they would be the legs. So we'd set 8x plus 19 equal to 12x plus 3. And I'm going to go ahead and get my x's together here. You'd have 19 equals 4x plus 3. Subtracting 3 leaves me with 16 equals 4x. Divide by 4. X is 4. So solving for x in both of those triangles, this time when they were on the sides. So now let's look at a corollary to the base angles theorem. A corollary is an extension that comes off of it, a fact that is true. If a triangle is equilateral, then it will also be equiangular. So the idea that if it has 3 equal sides, using that same idea of equal sides being across from the equal angles, that means that if it has 3 equal sides, we're guaranteeing that it's going to have 3 equal angles as well. So using that knowledge, let's go ahead and think about what's happening here in number 5. I have 3 equal sides. That means the angles will all be the same. Now I want to be careful. If I set 4y equal to 5x plus 25, that's true, but so is 32z minus 4 equal to 5x plus 25. I have 3 variables to solve for. But you do know that there are 180 total degrees in a triangle. And if all 3 angles are the same, that means each one is 60 degrees. So I just set each piece of information or expression equal to 60. So let's start with x. 5x plus 25 equals 60. If you subtract the 25 from 60, you get 35. So x would be 7. Now let's do the same thing with the y. The y is 4y equals 60. Divide by 4, y is 15. And now 32z minus 4 equals 60. Adding 4, I end up with 32z equals 64. Z equals 2. So there we go. We have 3 variables. We've solved for each of them using the fact that if a triangle is equilateral, then it's also equiangular. And corollary to the converse. Well, again, if we flip around that statement, what if a triangle is equiangular? Well, if all 3 angles are the same, then it has to have all 3 sides the same. So knowing that, we want to find the perimeter of this triangle. So we have 9x minus 11, 6x plus 16. Well, I'm noticing that all 3 angles are the same, that means the sides are the same. That means this side is the same as this side is the same as this side. So that means my 9x minus 11 side will be equal to the 6x plus 16 side. And now we'll go ahead and solve for x here. We'll end up with 3x minus 11 equals 16. Add 11, we'll have 27 equals 3x, so x equals 9. Now with that in mind, it said find the perimeter of the triangle. So if we go ahead and place that 9 in right here, 9 times 9 is 81 minus 11. Think about what that number would be, ladies and gentlemen, right there. 81 minus 11. Okay, and also do the same here. But think about that too. Would these two be the same? Yeah, they would, right? So we'd end up with this one would be 70. This one would be 70. This one would be 70, right? You don't even have to plug it in that other one if you don't want to. Plug it into one of these. So 81 minus 11, 70. Each piece is 70. So what's the total perimeter of that triangle? The total perimeter of that triangle would be 70 plus 70 plus 70, or 210. And I'll label that centimeters, okay? So solving for x using the idea of pieces that are equal. I want to thank you for taking good notes today and filling out that foldable. We'll continue practicing with our properties of equilateral and isosceles triangles. Thank you.